Okay. Okay, so as we look at our Canvas course, I'm going to actually switch over to student view so that my view is consistent with what you guys are seeing, because obviously as an instructor I see other stuff. Okay, so so first and foremost, whenever we have our Friday work independent days, I want you to know that you have to have all the homework done. Okay, not just a piece of homework from that learning plan. It has to be all of them. Okay, so if you are missing anything from our first module, then you're not eligible. And even if we're on to the third module, you're not eligible to not be here. Okay, that's not an excused absence. So so everything has to be in and caught up in order not to have to be there. Now that's on the work days. This week, because we missed Monday, Friday is not a work day. It is a regularly scheduled lecture. So you either have to be in person or virtual live, okay? Because we are going to be going over things. We just lost a day, so we don't have that extra day. And we'll always kind of know week by week if that Friday is a work day. My hope is it's always, but it may not be. So don't like plan like, oh, I don't have to go to school on Fridays because, you know, it's always a work day. Don't plan that necessarily. It's been working out, okay? But this week it won't be. And then going forward, we'll always kind of know on Wednesday what Friday looks like, okay? So kind of plan that. So I want to go and I want to look at the grades so that everybody knows where to go. So over on the left-hand side, here are the grades. You want to click on there. And it's going to list anything that is an assignment. And if you don't have something in by the due date, okay, so if the due date has passed and it's not in, notice that I'm a test. This isn't anybody's grades, just so you know, this is just a test student. You'll notice that I have missing items here. I would not be eligible to not come on Friday, okay? I also want to make sure that we all know that there was 3 assignments for module number 1, okay? So we had the drawings for chapter 1 in AutoCAD, the drawings in chapter 2 in AutoCAD, and then we also had, I called it it was meant to say review questions. It was like an online Canvas thing, okay? And you got to make sure you have all 3 of those done to say I'm done with module number 1, okay? Then module number 2 had 2 items. There was the, I'm going to kind of hold it up here. I don't know if those who are online can see. Those were the orthographic projection things, okay? And there was a number, it was kind of like a workbook packet, you know, that you had to do. And those need to be hand done, scanned, or taken a picture and then uploaded to that assignment, okay? So there was that. And then we also did have an orthographic projection practice which was, I'm sorry, the chapter 3 drawings from the AutoCAD book. So each one of our modules, you'll always have AutoCAD work to do, whether it's 1 or 2 chapters, and then they'll also be out of that tech drafting book. So right now we have 5 assignments where module 2's due date would have been last week Friday, and then the previous Friday for the module 1. So if you go into your grades and you're missing anything here, now you won't get any late points taken off, but the deal is, in order to get that, you know, Friday or our work day that you don't have to physically be either virtual or in class, you have to be here for those, okay? So the only way you get kind of the pass on Fridays or that work time is if you have everything caught up, okay? Are there any questions about that? Now, if you have missing work and you just, you know, don't do Friday, or you say to me, oh, I'm not going to be there, it's an excused absence, but there are points that are going to come off your grade because you don't have all the stuff in, okay? So it's a way for me to just make sure that you're keeping up with things. It's your incentive to do so. So you get a reward when you're caught up, but it doesn't mean that you're not getting points off if you're not doing what you're supposed to. Okay. And so just know that's the intent for Friday. So I want you to have time available and that you're keeping up with things. Okay. So any questions about that? Okay. All right, so I just want to be sure we're all on the same page, because sometimes, you know, we get a lot that first week, especially if you have multiple classes, a lot of different ways students or teachers are doing things. And I am trying to be as flexible as possible, but we do have boundaries too. Okay. So so let me know if you have any questions or concerns, or you're unclear about your grades and how they look. Okay. So so I want everybody by the end of this week, by Friday, to have everything in. Okay. If we have the ability to do that, if everybody has everything in, now I will never say who doesn't have what, don't worry about that. But if we do, then maybe, I don't know, 8 o'clock in the morning. Donuts always sound good, don't they? So so encourage your classmates. Hey, do you have your tech drafting in? We want donuts. Okay, so our goal is to have everything in by the end of this week, and your incentive is you get food if you come. Okay, usually that works. I don't know. I've done that before, and it's a pretty good incentive. So be focused on getting these things caught up, especially since we're finishing up our 3rd week. There's only 8 weeks that we're going to be working on. I don't want you guys to get too far behind, because sometimes we can look at these things and say, oh, I got it. I'll just get it in later. And then all of a sudden it all catches up, and it's a lot. Because remember, as you're moving along, these first weeks in almost every class might seem light. Okay. But as you go along, it starts all of a sudden getting heavy, and then it's heavy in all of them. Okay. So so just I want to encourage you to keep up with things, and I want to be sure that you know where you're looking in Canvas, because I know it may be new. Okay. If you do have any concerns or any comments about that, you can either email me, or we can meet, or whatever. Okay. So so I want to be sure that you're up to speed on that. And then as you know, the modules are where we're going to be kind of landing. So I'm going to go out of the leave student view for right now, go back to my regular view. And this is very similar to what you see. You'll notice that we're going to be down on module number 3, and we're going to be looking at the agenda items that we see here. So today, our first session is going to be going out of that tech drawing book. And I have the PowerPoint here for you to reference, and I'm going to be using this as my guide, if you would. So if you wanted to pull that up on your screen and kind of follow along, I'll have it here, and I'll have it on Zoom as well. Now, additionally today, last week I told you, make sure that you have a flash drive available, because we're going to need it going forward. So so hopefully everybody brought it. If you didn't, you can always save these files on your OneDrive, but I don't know. OneDrive sometimes scares me. It's like elusive. It works sometimes, it like seems to be there, and other times it doesn't. If you're somebody who gets it, that's awesome. I like cross my fingers every time I go into the OneDrive and just hope for the best. And most of the times it works out, but sometimes it doesn't. But we're going to be going on to just starting our session number 2, and it's going to be creating a template in AutoCAD. Okay. And this is important, because going forward, from this day forward, we're going to be using these templates, and you're going to be responsible for line types and layers and line widths and all that kind of stuff that is going to fit the standard in creating drawings. Okay. So so we're kind of adding that to when we're doing our drawing. So I'm always going to be checking to be sure you have those. So I want to be sure that you have all the information for the templates. Okay. So we'll be referencing that a little bit later today. So we'll need our jump drive at that point. Okay. So so just going back a layer, and we are going to start with module number 3, session number 1, and we're going to pull up that PowerPoint presentation, and I'm going to use you know, this here to kind of guide us through. So if you want to open up to chapter 7 in your book. Now, depending on the version that you have, if you chose to get a older version of the book, that's okay. All right. But I don't think it lines up with chapter 7. You may have to look for the chapter that says 2D drawing representation. Okay. So I'm not exactly sure what that is, but it may be different. So I'm not going to read all these objectives to you, but we're going to get into a little bit of the nitty-gritty of how to show certain types of features appropriately in drawings, kind of like start the rules of how we're going to be showing our views. So this is very important. And the reason it's really important is because, as you know, as a designer, your job is to create that documentation so that parts can be manufactured. And you're creating them in a way and using a graphical language truly, and you're using a standard graphical language so that other people in other companies, other departments, other countries can be able to figure out what you're trying to do and say, so that ultimately when they make that part and you bring it together in the assembly, it's going to function and fit appropriately. Okay. So they have to be able to, understand what you're doing. So like I said, this is going to be more that, if you would, kind of that nitty gritty of how do we show different things. So when we have manufactured parts, we're inevitably going to have different types of features. Okay. So once we kind of identify some standard features as we see here, and we're going to kind of go through each one of these and talk about them, then there's going to be the job of how do I represent them on a 2D drawing. Okay. So over on the right-hand side here, they have kind of this assembly, and you'll notice that they're pointing to different items. So as we go down our list on the left-hand side here, starting with fillet, we're going to see fillets over here. Okay. And then rounds, we're going to see rounds over here and such. So I'm going to start here by looking at a fillet. A fillet is going to be an internal intended rounded corner. So it's something that we're putting a little round, and we've done a little bit of this already on the AutoCAD drawings that we've experimented with. AutoCAD actually has a nice little feature that does it for us automatically, right? So fillets are always going to be internal rounded corners. Okay. Now it says here they strengthen kind of the interior. So when you get to strengthen materials, you're going to find out when we have really sharp corners, those create what we call as stress concentrations. If we can round those corners, there's less stress there, and high stresses are going to be places where we're concerned about something prematurely failing. Okay, so we want to minimize those as designers. So it is desirable to do rounded corners, interior corners, rather than sharp corners whenever possible. Okay. Now, a round, on the other hand, is very similar to a fillet, except it's on an outside corner. So we're rounding off a sharp corner, if you would. Okay, we're gonna see this a lot when we have castings, for instance. We round corners because they're easier to create in a casting. They come out of the casting a little bit better. And so we see those on there. But you can also round, machined corners as well. Okay, so it's just called a round. So if we go over here, we should be able to locate fillets and rounds. So fillets is on that interior corner right here of this base. And there's other ones as well, where this flange comes down. There's an interior rounded corner. They're just pointing to one, for instance. Okay. Same thing on the rounded edges. This looks to me like it's a cast piece. So anything that's an outside edge is naturally going to have a round on it. Okay. A counterbore. A counterbore is a cylindrical recess around a hole. And it's intended, I like to say, to bury the head of a bolt down below the surface. Okay. So if we look, let's see here, do they have a counterbore? Yeah, they do. It's a little bit dark, but maybe it's easier to see here. This you'll notice is a larger diameter that is, and I hate to use the word, it's counterbored down, but it's down for a depth, and that depth is specific to be deep enough so that the head of a bolt is now going to be down below that surface. Now, we may do that for a couple of reasons. Number one, something might interfere. Something might be in the way if it's sticking up. Okay. The other reason we might do it is it looks better. It just looks better. Okay. So that's what we call a counterbored hole. Okay. Then we've got a countersink. A countersink is going to be another type of a recess that we put in, but this time we're at an angle. And that angle is going to be specific for what we call flat head screws. They kind of, or machine screws, if you know what a machine screw is, it kind of comes at an angle, and then the threads are down below. So when you drop it in place, now this angle matches. And again, you're going to have then the head flush with the surface that you're on. Now, a spot face is a little bit different. It's sort of like a counterbore, but we don't go as deep to bury the entire head of a bolt. What we normally do with a spot face is we create just a nice little machined surface so that in this case, you'll notice that it looks kind of pitted and rough. It's probably a cast surface as I just kind of look at the model. And on a cast surface, it's not going to be consistent or really super flat. So what we do is we spot face an area where we need to have contact, for instance, with like a washer or a bolt. We make it large enough so now it has a nice seat to you know, sit on, and then also make sure that it's lined up with whatever it is. Now, a boss is going to be a raised area. Sometimes in this case, this is a boss that is on a slot, but we could have a boss that's coming up a little bit and it's a round. That's how it's normally, you know, seen or seen very often. And again, that's just a raised area on a casting that is then going to probably receive or seat something on it. It's called a boss. A lug. I think I refer to this more as a foot, a protrusion, you know, of a surface. To me, as they call this a lug. I think it looks like a foot. Okay. So just another way to see like a protrusion that's coming out. A flange is going to be a flattened collar or a rim around a cylindrical part. Okay, so a flange, for instance, is going to be this part right here. So it's kind of a larger area. And sometimes there might even be bolt holes in there that you're connecting with something. So that's a flange. A chamfer is going to be, instead of a rounded corner, it's just kind of sliced off, many times at a 45-degree angle. Sometimes we'll say chamfer edges to break sharp corners. Okay, and that's really just to do exactly that, to just kind of take the corner off so that as you're handling it, especially machined parts, if you have those sharp corners, you can like cut yourself, okay, if you're not careful. So chamfers help with that. They also provide sometimes as an internal a lead-in for something to fit inside, easier to get in. The next one is a neck. This is going to be a small groove that's cut around a diameter, often used when we change diameters from one to the next. Okay, sometimes we might neck down in order to put like a collar in place or something like that. Okay. Keyway, key seat. This is the shape. It's gonna, they say here, a depression cut along the axis of a cylinder. And this is going to be so that we can engage with another element so that it is going to be rotating at the same RPMs. So a key would fit in here, and that key would, half of it would sit in the seat that you see here, but then it would be tall enough to be up above, and then now it's going to receive into another part. So for instance, a gear, when we mount it to a shaft, is going to have a keyway in it. It's going to mate with the key seat on a shaft, and then now the key in between allows it to rotate at the same RPM as that shaft. Okay. A knurling is just going to be a pattern that is going to be on the outside of a shaft that is going to have like texture. Okay. Many times knurling is going to be used so that it provides a grip, okay, on something. So if you've ever had tools, for instance, and you know, one part of the tool, maybe where the head of the tool is, and even the shaft of the tool might be shiny and smooth, but the part that you need to grip is more rough, so that you can have a better grip on it, doesn't slip out of your hand. Okay. So that's what knurling is. And then finally, here's a bushing. A bushing is going to be an element that is going to allow rotation, one object relative to another, that's going to be nice and smooth. Many times bushings are going to be replaceable. They're made out of like brass or bronze, and they allow kind of a protection, if you would, on the actual surface of the shaft. Okay, so this isn't anything you have to memorize, but as these common types of features come up, you'll kind of have a better idea of what they're referencing, especially if you haven't had the experience of being in manufacturing or building things. Okay, not a requirement here. So if you have had that experience, then these sound a little bit more familiar. I'm going to zoom out a little bit. So now let's start looking at how we're going to represent, you know, common features properly to the standard. So I always want to emphasize that everything that we do, everything that we show is in the ANSI standard, and the ANSI standard is written out there for like the world. Okay. And so if you are in manufacturing here, the next state over, like I said, anywhere in the world, drawings are made to the ANSI standard. There are graphical communication language so that everybody is on the same page. So even if you don't speak the same language, the way you lay something out and how a drawing looks in proper projection and shown properly for the features that we'll be talking about here people will still know, what you're trying to get across. Okay. So first of all, we're always going to have our drawings in standard projection, and we got introduced to that last week. So this is where we start with that front view. We project a top, we project a right side. We have choices of left, bottom, back, and so on. Okay. And we always pick the 3 views in projection with one another that are going to give us the best picture of that particular part. Meaning, it's a good idea to start with at least 3 and kind of analyze it. Is 3 overkill? Is this part super simple? Can I get my idea across in 2? So you want as few views, but you want to be able to show the part in 2 views. Meaning, I want to show it in 1 where I see it as its full size shape, and number 2 in another view as a hidden feature or as a side view. Okay. So for instance, when I look at this part, this is our isometric, if you would. And you'll notice that we have the cylinder coming up, and then we have the flat plate part kind of connected to it going out the bottom. And as we look at this, if I'm trying to decide how many views that I'm going to be creating, I have to be able to see each one of those features as their true size and shape. Okay. Meaning, if this is a cylinder, I better see a view somewhere that has it as a circle. So I have to use the top view. Okay. Just for that feature alone. And then as I look, okay, not only do I need to know its shape, its round shape, but how high is it? Well, now I get some choices. I can, see that height in my front view, and I can also see it, you'll notice, in the right side view. Okay. The better view though is always in the front view in this case, as you can see. And again, notice everything is in projection. We're not offset. We're not, in a different place. If I choose my front view, the only views that I can have adjacent to it in line are the top, the bottom, the right, or the left. I can't add a back view and put it on the side of the front view. Okay. Because it's not in projection. Okay. I can't skip a view, if you would, in between. Remember how we unfolded that glass box. Okay. Now, whether I pick a right or a left depends on, do you remember the rule? Those views are going to look similar, but what is my rule for picking a view? The fewest number of what? Now, I don't see any here, huh? The fewest number of hidden lines. So as our parts get more complex, we are going to have more and more hidden lines. And so we pick views based on the fewest number of hidden lines, especially if they're going to be similar. Okay. All right. Now, as we look here, you're going to notice on this part, the sides of that plate on the bottom don't align or aren't tangent with that cylinder that's coming up. So it's actually not quite as wide. So there is going to be an edge that when it actually meets with that cylinder, you're going to notice that there is this point right here in the top view. That's going to literally create an edge going down that we will see. We need to represent that then in the front view. So notice how that is in projection. Okay. On the other hand, if we have it where the plate is wide enough to be tangent in that front view all the way back, that becomes a blend at the bottom. It's it's not really an edge that we see. So now notice that we are going to show the edge go in until it hits the center line where it becomes tangent. But notice we don't have that line coming down here because it's a blend. Okay. It's a tangency, and we don't show lines for tangencies. Okay. Questions as you kind of peek at the 2 differences here. Okay. Now, the next one is visualizing and drawing complex cylindrical features. So they're really going from the 2D picture that we see down here. There's 3 views, all right? And without looking at, kind of this diagonal steps, if we look here early on when we're in this field, and especially if you haven't really worked much with orthographic projection before, looking at these 3 views might not be all that easy, okay? So it takes practice. It takes a little bit of time, and we do a progression of kind of from easier parts, through. And the advantage that you get as a mechanical designer is as you're learning this, you're also creating the parts. And then all of a sudden, as you're creating them, it starts to click more and more, and it gets easier and easier. And this is where, for instance, you as the designer, if you're utilizing parametric drafting software, And AutoCAD is not that. Okay. When you get to your parametric CAD classes and you're using Creo, Creo is going to be that 3D parametric modeling. So on your drawings, when possible, and you have the room, always add that little up in the corner isometric view so that it gives you clarity of what that part looks like. So that's always something that you can also help other people out who are going to be reading your drawings. But this kind of takes it from the perspective of, okay, let's kind of start with the outside. And we'll notice that we have this arc over the top. So the very first step here kind of takes the if you would, like a block of material and takes those top corners off. So this is what the outside looks like. And we have a little bit of thickness here, right? Then the next part notices, the next step is, let's take the hole out of the center. And as we look to the side here, we're going to see that that hole goes all the way through. So it's kind of like pulling that material out. And now we've got this block with an arched top with a hole through the middle. Then you'll notice the next feature that they look at are these counterbore holes. Let's take those out of the front to make room for, and this is really, you know, those counterbore holes end up looking like bolts, but this is taking that material out and pulling it away. And then the last feature that we have here is like this little chunk, you know, out of that portion. So you can see where they're taking that away. And so this ends up being our final 3D view of that part, okay, from the 2D views that we see here, okay. Visualization, don't expect it to be like this. It takes a little bit of time, all right. Now, cylinders when they're sliced. So these are nice views because sometimes it's like, how do I draw that? And we're going to have, you know, shafts that are going to have flats on them, or, you know, in the case here where we have cylinders where we're going to have steps or cutoffs. Okay. So this is giving us a good view of how we would see those. Now, I'm not crazy about their orientation, but I believe they did it this way to save space on the page. As a good practice, remember, we want our front view to run horizontally with our longest dimension and give us the best, you know, look at the shape. So to me, this is going to be the front view. And I would actually, you know, go 90 degrees here and have that, you know, lengthwise. But they have the front view here. They have the top view directly above it, bless you, and then a right side over here. I'm not going to say it's wrong, but there are better ways of kind of getting at it. But again, I think they're just trying to save space. So don't worry so much about that. So you'll notice here that as a cylinder, a complete cylinder, they've got a cutout here. So looking straight down, here's that cutout. And then from our front view, we see how deep that's going to be, and it creates that edge. And over in the right side view, now we see the actual like shelf or the depth of how far it's going to be. Okay. Over here on the right side, we've got some steps on a shaft. So here again, kind of starting with that top view, here's my circular view. And as I look to the front here, now I've got the steps here. And then over on the right side view. In both of these cases, the way they have it drawn out, you need the 3 views so that you can get the full look of the entire shape of the part. Now, you might be like, well, you can see the cutout depth and how far it goes on these 2 views, but you don't see that it's a circular cylinder until we look at the top view, that this is actually a round part. Okay, so 3 views are necessary for both of these, and I'm actually all 3 when we get to the third one. Okay, so you always want to give a good pictorial of what it actually looks like. Okay, and then over on the right hand side here, we see the pictorial on here. We're taking a slice off the top, so this is going to be our top view. This is going to be our front view looking straight on, and then here we've got our right side view. Okay, so any questions so far? Okay. All right, cylinders and ellipses. So when we, for instance, cut off a cylinder at an angle and we look at it, we're gonna notice that in some views it's gonna be elongated, or we're gonna be creating an ellipse, what we call it. So you'll notice here that in this first one where we cut it at an angle, when we look straight down on it, it still looks like a cylinder, you know, like a round circle, but it's when we look at a side view is where we get this ellipse look. Okay. On the next one here in the middle, this is just really kind of having a cylinder, not looking straight on in any one of the views. And then noticing that, you know, we get the ellipses as we look on the side. The nice part about CAD software is it'll create the ellipses for us, okay? When I was doing it manually, there are instruments, and you may have come across these called like French curves where we can create these, okay? And you can plot the points. But CAD is going to help us along with this. So ellipses are used when we have kind of those elongated cutoffs. Bless you. The next one is looking at intersections and tangencies. Okay, so I'm gonna kind of come in a little bit closer here. So in each one of these cases, you're gonna notice that when we have tangencies, most often the rule is that we don't show the line in another view because it's a blend. Okay, so here we have a rounded corner, for instance. Here is the front view where we identify the rounded corner. We would actually dimension here, and then this point right here, again, a tangency is a blend. So there isn't a physical line that occurs, okay? So notice that we don't show a line in the right side view and we don't show a line in the top view, okay? So this is how we would show that. The next one that we see here, on the other hand, we have like this radius cut out here, and we do get a sharp corner or an edge. In both cases, top view, right side view, notice we show those edges, okay? So here's the line for the edge here, and here's the line for the edge here. On the next one, we've got kind of a ski slope, if you would, that's coming down. So notice the portion where we have the blends for the tangencies, no lines. But where we have the actual, foot at the bottom here, now we've got an edge with a line, okay? Now, when you have a vertical surface, though, this one is more of a sloped surface. When we have a more vertical surface where we actually can see a vertical line coming down, even though we've got the blends going in and out, we draw that line in the top view then to show that, okay? Let me see here. As we go back, this one is similar to that very first example. I'm not sure why they don't have hidden, or no, this is a line here, but this part should be hidden. That's going back in. I'm not sure why they have that squared in there, but that should actually be hidden based on what I believe the part looks like. In this case, too, this line would not be there because that's a blend into the surface. I think that might be a mistake. Same thing here. That line should not be there. And then you'll notice that where it comes across is where the actual line stops, and then it extends in the back, so we get a hidden line in the back. But this line in the top view, those need to be gone in each one of these cases. Now, the very last view, H, looks fine to me. So here we have a radius. We've got blends here, and then you're going to notice that they did identify, because it's more of a vertical surface here that's in the middle, they do identify that as an edge up in the top view, and then this extends over just because it blends down in, and you wouldn't show a tangency at that point. Okay, so I'm not expecting you at this point to remember each and every one of those, but I want you to know that in this chapter 7, when you are expected to represent different types of features like this is a place to go back to see what's correct or not, okay? And that's the reason for having the textbook. Out in industry, or even as you kind of make your way through the program, you're not going to remember it all the time, okay? So, so having the textbook and be able to go back and see some examples that are similar to your application is going to be important. Here we have some intersections of cylinders. So we have two cylindrical features coming together. We want to recognize that as well. Now, the difference here is that we have a small cylindrical piece coming into a larger one, and here we have a little bit larger one. So we represent it two different ways. You can either do no curve where it just comes and the edge is there, or you can blend it and show it going in this direction like this. I will tell you that in AutoCAD, even I tend to do all cylindricals, whether they're larger or smaller, that like we see on the left-hand side, because otherwise you'd have to take the time to construct it. And sometimes it's just not that big of a deal. When you do parametric software like Creo, it's going to automatically put those in there for you, okay, when they're appropriate. So, so don't worry about that too much. Doing a straight down is totally fine. Fillets and rounds, we've been seeing those as well. So, so you'll notice here we have some what they call round outs. This is where when we blend into surfaces, but we have these rounded surfaces like on castings to get there. So you'll notice here we have kind of an L bracket with a rib in the middle, but you'll notice that based on based on the pictorial here, this is like a cast part. So everything has rounded corners and it has those interior fillets. So how do you show those? Because when you stop, they kind of flare out at the bottom to blend into that surface. So we do exactly that. So you're going to notice that we have these little radiuses that are going to round out as we see it on the surface. So there isn't a line here because, you know, it's rounding down into that. It's a blend as opposed to an actual surface. So that radius is going to correspond to the radius for all of those rounds and fillets on a drawing. And we've seen it on one of the, I think it was in the last assignment that you had, where there was a note like all rounds are blah, 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 unless otherwise noted. So if there's something that's undimensioned, but you can see it as a round or a fillet, there's usually a general note so that you don't dimension each and every one. Because in this case, there's a lot of them. And then all of a sudden you're cluttering up the drawing with all of these dimensions. So general notes can be used and you would know what that size is. And typically it's going to be the same for most all of those different values. And then our round out radius will correspond to that size. Okay. So these are some nice examples of, you know, different arrangements that we see there. Conventional edges. Now, this one kind of is the exception to some of the things we've been talking about. So for instance, we don't have, this is kind of a standard structural shape here. You'll notice that we don't have a vertical in either one of these directions. So by kind of the rules we saw earlier, we wouldn't put any lines in that right side view. But when I look at this, it's deceiving. It looks like there's a flat like plate that we're dealing with as opposed to this structural surface. So you'll notice that you do one of these two things. So preferred in large sizes is just to add a line so you can see that there's a difference there. And then the same thing at the bottom. Okay. And then when you see that right side view or that front view, if you would, that cross-sectional view, now it seems to make sense and it corresponds. Okay. Same thing over here. You could do two lines if you wanted to, probably a little bit of overkill, but that middle one, you'd at least want to put a line or two to more, you know, more specifically specify it to bring clarity, if you would. Okay. To bring clarity. As we look down here, here are some rounded and filleted intersections and when and to and when not to eliminate the or put in the edges. So in this case too, you've got blends with rounds and fillets, but notice you've got kind of this sharp V there. Again, if we would leave it off, it would look like it's just a flat piece, but we do want to give a good clear representation. So in this case, you would add it. Okay. In this case, you're going to notice too, we have blends from the very top all the way down and showing those kind of, you know, dimensions or those circles as they progress to get larger is much more clear than showing nothing. Okay. Because this looks like it's just a flat disc by looking at that top view. Same thing here when we have, you know, this rounded edge here or this half circle. Again, we're depicting that there is some depth there, you know, look further. So then you're going to get that detail from the front view. And then the same thing here for like, it looks like a dish that's going down in the inside. You know, adding some of those edges just gives clarity to what it actually is. Okay. So, so any questions so far? I know, not the most exciting subject here. Probably even trying to keep your eyes open at this point. Not going to lie. That's okay. We just need to get through it. We need to see it because then the next time when it comes up, you're gonna be like, oh yeah, I kind of remember. I'm going to go back and I'm going to look what that looks like. Necessary views. And we've been touching on this and this will continue to be reinforced. We want to have the minimum number of views that is going to get us the true size and shape of a feature in at least one view so that we can dimension it. And we want to show it in another view as a hidden feature so we can show its relationship to the other things. When kind of starting and determining, start with those three views and see how it looks. And then after that, if there's a view where you're like, there's barely anything over there, or I didn't add any dimensions over there, then it might be a clue that you don't need it. Okay. But otherwise start with those three views, front, top, right side, or left side, and kind of go from there. Okay. Then there's different types of views. And again, this is going to come when we've got more complex parts and different types of things. And we'll touch on this in the weeks to come. But this is a partial view where, for instance, we're seeing these two features on either end, and we're showing a look of them, but we're not showing the entire view down below. Now, this practice was much more prevalent when we had manual drafting. Okay, for obvious reasons. If you had a part that was really complex, it kind of saved time in not having to draw the rest of the view, but you got the part where that now I can say, here's the diameter of the hole, here's the diameter of the outside of that boss, okay? And then the other details can be for another view. But now with parametric software like Creo, which is going to be the primary CAD software that you're going to use, now all of a sudden, the computer generates the views for us after we've created our model. And it's not as much of a time saver to do things like this. So we may not see them quite as often. You may not generate them quite as often, but this is what they are. Okay, so there's to save space and time. Okay. Showing enlarged views. These will come up because at times on a drawing, when we show them as their standard size and we try to dimension them, it's too small in there. Okay, so what we'll do is we'll look at this portion right here. So you'll notice that we've got view B, and then down here we enlarge it, we make it bigger. So now we can see more clearly what all the details are. Okay, so enlarged views or detail views are going to be something that we will encounter from time to time. We can also break things. So when we put something on, for instance, an 8.5 by 11 piece of paper, but my part is really long, okay, I can't make it super small on here to dimension the length. What I can do is so that I can add detail to the form of the part along its perimeter, I can break the actual part to let people know, like, this isn't to scale, all right, but I'm going to add the other details where needed. So you'll notice here for a round part, that's the type of break that we do. For a round tube, we do kind of the, I don't know, my coworker used to call it the Fred Flintstone hem at the, like at the bottom of his outfit. Here we've got a tubular round. Here's a rectangle, rectangular wood. So different ways that we can do that. Those are called break lines. Now, alignment of views, as we know, first and foremost, orthographic projection is always in play, like always in play, okay? Orthographic projection. So when we have a front view, for instance, we have a top view, it has to be in alignment. So if we take and we look straight up, center lines are in alignment, the lines that are on the edges and so on. So this is not okay. The second and the third ones, notice that the views are not in alignment, not in orthographic projection. Okay. So if you ever get on a drawing that you send to me, I'm going to put orthographic projection, and I may not say, what's all wrong, but look back and is your stuff in alignment? It may not be. Okay. And that's a big deal. Like that's job number one. Got to have them in line. Okay. So make sure that you're doing that. And again, when we get to 3D CAD, I don't want it to sound like, oh my gosh, I can't wait. I want you to look forward to parametric designing because it is fun. And there are many automatic or automated things that can happen, but you are still the designer. You are still the decision maker. So you have to know this stuff because there's going to be things that the computer is going to allow you to do that aren't to the standard. Okay. Or it's going to put dimensions on things in the wrong views. So you have to fix them up to the standard. Okay. So you're still this thinking person. The machine hasn't taken over yet. Okay. So understanding and doing this, and that's why we do this information here. We first get to know the standard. We practice it using AutoCAD, kind of more that 2D, type of thing where we're doing more construction and placing things intentionally so that when we get to the tools that can make our job easier, we can also make the documentation correct into the standard. Okay. All right. Removed views. These are going to be views that actually we can create that are going to be off to the side. So this is the exception. So notice the three views right here. I've got a front, I've got a top, and in this case, I have a left side view. But to get the details of this boss and the size of the hole and all that kind of stuff, you'll notice that I end up having hidden lines here, okay? And one of the rules that we're gonna learn is that you cannot dimension to a hidden feature. So if I would try to put my diameters in this view over here for that, you know, feature right there, it would be illegal, okay? Because I have a hidden view that I'm dimensioning to. I can't do that. So instead, you'll notice that I'm going to create what we call a view, AA, okay? And I'm going to then place it somewhere else on the drawing. It is not in alignment here with anything. And the reason it's not is because it's not one of my principal views, okay? So I have to have it offset. I have to have it somewhere else. So notice that this center line is not in line with the top, and it's not in line with that left side view. Okay, it is intentionally offset, and that is a rule. Okay, because we're adding an extra view that is not one of our principal views, but we need it to dimension something so that we can actually, you know, see that true size and shape to add a dimension to it. Okay. Right hand and left hand parts. So in this case, sometimes this may come up where you have a one side of a part, it's identical, but it's really the mirror image, and it's called the left side, right side. Okay. Sometimes we have drawings that are going to have both on the same drawing. Not a great idea by company standard, because really each should have their own part number, but you may see it as exactly that, right and left hand sides. So that's just really kind of showing that mirror image on either side. Revolution conventions. We're not going to see this most immediately, but when we have parts that have ribs on them or are spoked, okay, we're going to find out that the way that we draw them, even though it's not in technical orthographic projection, we draw them so that they're more easily interpreted. So as we look at this front view of this part that has the ribs on it and has the holes, when we look at, for instance, the right side view, the correctly or to the letter orthographic projection is going to be this right here. Okay. Notice that on the top we see the rib, but on the bottom here we see it kind of foreshortened. The way that we actually draw it is we take that rib and we strike that arc, we bring it around, we rotate it. So now we see it as a full rib. They're evenly spaced around that diameter. So we are going to show it in that right side view so that we can see that it's a rib that's the same size on either side. Okay. This is just a convention that you have to get to know. All right. It may not make a whole lot of sense, but it looks more clear and represents better what this part is actually doing. Okay. Now, if you have a rib coming straight down, you don't have to worry about it. Then it'll project the way it's supposed to. But when we have them, for instance, where we have them 3 evenly spaced around, these guys at the bottom here are foreshortened. So we make it so that it evens out, if you would. Okay. Same thing with a spoked part as well. We pull that bottom spoke around so that it's going to be 90 degrees or 180 degrees from the other one. And we make it look like this so that, again, it gives the more realistic idea that this is an even part all the way around. Okay. All right. And you would have both views to see it. And this is a convention. Okay. So it's not something that we just randomly came up with. Common hole features. Okay. There's all different types of holes that we're going to have in parts. And as we go through and we design, we're going to be noticing and calling these out. So this is a great introduction. So first and foremost, we have a drilled, or what we call a blind hole. This is going to be a hole that is going to be drilled to a specific date. Or a depth. You have a diameter and then you have a depth, and it doesn't go all the way through. So then we also we bottom out that what would be like the drill, and we give it a point. Okay. And you'll notice that the call out up here for a hole will always be a diameter symbol. That's going to be that circle with the slash through it. That means diameter. Okay. Capital R in front of a number is going to be the radius. Okay. And then immediately in back of it, you're going to see this horizontal line with an arrow going down. That means depth. That's a symbol. Okay. And we always default to symbols because, especially if we are sending our prints to other countries where we might not speak the same language, symbol you know, can be known across different different languages. So so we always default to symbols when there's one available to us. We never make up symbols. We have to use whatever the standard has, and you'll continue to learn these. And if not, then we do have to write it out as a note. The next one here is we have a drilled through hole. Now, in this case, they have it as a reamed hole. We no longer put on the drawing the manufacturing process, because sometimes you can achieve a size that is drilled. So you'll notice here that they have the what we would call the tolerance. This is going to go from 22.17 millimeters to 22.23 millimeters. Now, this is a very close tolerance, meaning the difference between the high and the low, and that's what's identified there, is really small, especially when we're considering millimeters. And that's why they'll say, oh, that's a reamed hole, but we never put that as a note on a drawing, okay? Because again, if you can achieve it with a different process, you know, go ahead. The next one here is a counterbore hole. Now, we already talked about counterbore holes, where most often they are going to be a feature that is created to bury the head of a fastener below the surface of a part, okay? So this diameter of the counterbore on the top is going to be large enough for whatever head of bolt that you're looking at. Now, there are resources and charts that are out there to give us, you know, what the standards are. So we're not so worried about size here, but just notice that it's larger and it's going to be to a depth that is then going to bury the head of a bolt. So you'll notice here that the top diameter point or 19 is going to be for the through hole, or the drilled hole that's going all the way through the smallest hole. And then the second line, that symbol right before the diameter of 29 is going to be the counterbore symbol, okay? And that's going to be the diameter. And then the number in back is going to be 14 millimeters deep, okay? As we move down, the next one here is going to be a counter sunk hole. And a counter sunk hole, as I said earlier, is for a different type of a fastener, and that is going to be for like a machine screw. If you're familiar, it has kind of those slanted sides, okay, and then the head is flat on the top. So so that's intentionally to accommodate that sort of a fastener. And again, that's going to have the head that's going to be flush with the top. So so you'll notice here that we have a V in front of that diameter, and that's going to be our countersink symbol. And then we have to tell it what the degrees are going to be, and that's going to be an included angle. So from vertical, it will be 41 on one side, 41 on the other. 82 is a standard for a counterbore tool. Then the next one that we have here is a spot face. A spot face is going to be very similar to a counterbore, except it's only going to be deep enough to clean up the surface. So there's not a depth identified here, because it's going to be dependent on whatever that surface looks like. So some surfaces might be a little deeper, some might not be hardly at all. And it all depends on, we just want to clean that up, make it nice and flat so something can seat properly on it. Okay, that's going to be a spot face. Now, as we look here, notice that each one of these views, as we look from the top, we're going to always dimension in the view where we see that hole feature as a circle. Okay, always dimension there, okay, including the depth. But then we always show in the corresponding, you know, view and projection where we see it as a hidden feature, okay? We don't dimension to the hidden feature, but we show it appropriately. Additionally, over in these last two views, you're going to show, what I like about this book is they'll show us the right way, but then they'll give us also, this is wrong. So down at the bottom here for counterbored and countersunk holes, you'll notice that they don't have the line going across where it changes diameters from one to the other. We need that line, okay? So kind of compare for the counterbore from here to here. So we have to have that line going across, okay? Because that is a surface as we look into that part, if you would, okay? Same thing for our countersunk hole. So these are gonna come up a lot. These are gonna come up a lot because we use holes for a lot of stuff. So the, I think this might be, oh, it's the second to last. So the second to last one here, this is kind of giving us a nice, like, view of a drawing, if you would. So here you're going to notice that we have the pictorial view up in the right-hand corner, and then we have the front view, corresponding top view and orthographic projection, and a right side view. Notice as well that all of our dimensions are dimensioned off of the part, okay, off of the part. As we start adding dimensions to things, there are certain ways that we do this as well, okay? And there's going to be some items that that are, I call them illegal, okay, against the standard. So so this is a nice representation. I'm not going to go too much into the dimensioning, but I am going to mention a couple things because they're worth talking about as long as we have it here. First of all, you'll notice that these dimensions, these are called baseline dimensions. And whenever we look at a dimension, this dimension line never touches the part. There's always a gap or a feature, okay? So wherever it's coming from, there's always going to be a gap. That one, that's a big deal. You'll also notice whenever we have a note or we have a dimension like this radius of 0.1, there's always a landing. So there's what we call the leader line that's pointing to it. It's at an angle. And then there's a landing, that horizontal little line, and then the note. So we always have landings when we're putting on notes or dimensions or callouts. So so those are there. Every dimension too, when it's not a baseline locational dimension like we see here, notice we have a 0, 0 up in the corner, and then all of these dimensions horizontally kind of give us their coordinates in that direction, and then vertically coordinates as well. This lends itself really nice, this dimensioning scheme, to when we have a manufacturing process that we know is going to be on a CNC machine, for instance, and it's based on the coordinates, okay? So that's really nice because it saves time for the operator later on when they're programming, okay? Because it's already figured out for them. I think that's it. That's all I'll mention for right now. And then here's one last drawing again. Notice here that we don't have 3 views. Notice that in this case, we got by with just having 2 and being able to dimension everything, okay? And that's okay too. So again, we want to think about where do we want to start, and 3 is always a good place to start, but then as you're drawing it as it's coming together, and then ultimately when we're dimensioning, do we need all of the views? Or you might have to add another view. It's okay to add a 4th or a 5th if you need to as well to get the information that you need. Okay, that's not unheard of either, to have a top and a bottom view, because we can't see a feature unless we look at it in that extra view. Okay, so so questions. Okay, finally we're at the last one. I know this kind of a lecture is kind of tough sometimes. I get it, but we just have to kind of get through it, and we did, we survived. So what I'm going to do is I'm going to stop recording here, and then we'll be back.